All right, so here we go with part 3 of section 4.7. This is our last example. It is about minimizing distance, and it reads which point or points on the graph of this function. Well, really, that's ugly notation. I'm sorry about that. That should really be x squared, are closest to the point 0, 2. That'll be fixed on your version. All right, so which of the points on the graph of that parabola are closest to the point 0, 2? Okay, let's see. This is a parabola that is opening down with a y-intercept of 4, so we're looking at something like this. And then we're asking which points are closest to the point 0, 2, so that's here, because remember that right there is 4. And so we're trying to find point or points on the graph that are closest. So like maybe there or there. And because of symmetry, whatever those distances are, they should be the same. Right? So if I zoom in on this, there's our point 0, 2. And these two values, there and there, are some xy where this distance is minimized. And then I'm pretty sure that this one over here would just be negative xy, the mirror image of that because of symmetry and all that. Okay, so I think I understand what's going on here. I want to find that point that's closest to the green point. The brown point that's closest to the green point. Right? Closest means to minimize distance. Now, I remember from a long time ago when I took some algebra classes, the distance formula. Distance is equal to the square root of x sub 2 minus x sub 1 squared plus y sub 2 minus y sub 1 squared. And so if we think of this as point 1 and this as point 2, then we would get that d is equal to the square root of x sub 2, which is, I don't know, x, minus x sub 1, which is 0, squared, plus y sub 2, which is just, I don't know, y, minus y sub 1, squared. And now we just need to minimize that function. Okay? I've got two problems here. One, I'm not sure how to minimize under a root, and also I have two variables. I have x's and y's. I can't do that. I just need one. So what I'm going to do is I'm going to find some other thing here and do a substitution. Now that some other thing here is literally already highlighted and circled for us. It's that y is the same thing as 4 minus x squared. And that's the substitution I'm going to use right there. Okay? So when I use that substitution, I then get this statement. D is equal to the square root of x squared, that's this first set of parentheses simplified, plus 4 minus x squared minus 2 squared. Let's see. 4 minus 2 is 2. 2 minus x squared squared. So this set of parentheses right here is going to turn into this, right? And so when I square that, I'm going to get 4 minus 4x squared plus x to the 4th. And then if I clean that up further, I get that d is equal to the square root of x to the 4th minus 3x squared plus 4. Okay, so now I'm to the point where I have found values for y that I could do a substitution, and I've got my optimization equation, my minimization, my equation I need to minimize, my function I need to minimize down to one variable. But I want to cheat a little bit further, because I don't like this, and I know that the next step is going to be to take a derivative, and that's going to give me a whole hot mess, so I'd like to ignore it. So I'd like to make the following argument. here's the argument I'd like to make. That if you were going to minimize the square root of a number, that's the same as just making that number as small as possible. So if the radicand is as small as possible, then the square root will also be as small as possible. Right? So as the radicand gets smaller, the root gets smaller. So I'm going to say, rather than minimize d, let's minimize d squared, which is equal to just plain old x to the fourth minus 3x squared plus 4. And if we just minimize that, then we don't have to deal with that root. And this is a legitimate approach in math, right? I want to minimize a composite function. I know that the outside function is the root, so if I just minimize the inside, the radicand, I'll get to where I need to be. Okay, so I need critical numbers. In order to get to critical numbers, though, I need a derivative. So I'm going to take the derivative of this. So the derivative with respect to x of d squared is going to be 4x cubed minus 6x. There's my function. Now I need critical numbers. Okay? Critical numbers are when that derivative does not exist or when that derivative is equal to 0. I can think of no values that'll make it not exist, but I'm pretty sure there's going to be some equals to 0 in there. So when is 4x cubed minus 6x equal to 0? If I factor that, that's going to be 2x times 2x squared minus 3 is equal to 0. So that means that x is 0. That's from this piece. Or that means that x squared is equal to 3/2, or that x is equal to plus or minus square root of 3/2. Okay? So here are my critical numbers. I have 3 of them. Okay? Now there is no reason that x can't be negative, so I'll keep those in mind. In fact, there are no limitations whatsoever on x. Now I'm not sure what the root of 3/2 is. So I'm going to go ahead and see if I can get a decimal approximation from my calculator. So I'll be right back with that. All right, that took a while in my time, but didn't take about a second in your time. I found my calculator. It was buried. This is approximately 1.22 and negative 1.22. I'll need that to find values to test intervals. Side note, that's new Roman numerals. Old Roman numerals would list 4 like this. If you ever get a chance to see a really old grandfather clock, look at 4 on the grandfather clock. They'll make their 4 like this. Right? Anyway, that has nothing to do with nothing. Let's test. All right. Let's see. All right, so interval number 1, I'm going to use negative 2. Negative 2 into that. Let's see. Negative 2 cubed. Oh man, I got to do some math here, don't I? Let's see, that's going to be 4 times negative 8 minus 6 times negative 2. 4 times negative 8 is negative 32 plus 12. That's negative out there. Now I'll check interval number 2. I'm just going to use negative 1. Right? Let's see, negative 1. That's going to be negative 4 plus 6, so that's going to be positive. Now I'll use positive 1 for interval number 3. Let's see, positive 1 is going to be 4 minus 6, so that's going to be negative. Okay. Interval number 4, I'll use 2. Let's see, 4 times, that's going to be what? 32 minus 12, so that's going to be positive. All right, so I'm confused. What does this mean? Well, this was a critical number. To the left, it was negative. To the right, it's positive. To the left, the first derivative was negative. To the right, the first derivative was positive, so that means it's some sort of a minimum. So we have a min at x equals negative root 3/2, okay. This was also a critical number. To the left of it, the first derivative is positive. To the right, the first derivative is negative. So that's a maximum of some sort. So we don't want that. Okay? So that's not good. And then this is our third critical number. To the left, the first derivative is negative, decreasing. To the right, the first derivative is positive, increasing. So that's also some sort of a minimum. So we have another minimum at x equals positive root 3/2. Now this isn't a bad thing. It's exactly what we expected, or what I expected when I looked at this. Because of symmetry, I would expect there to be 2 points where the derivative would give us critical numbers that were minimums. And so the last thing to do is to wrap it up and make it look pretty. Now, our job was to find the points on the graph. That's an x and a y. We only have an x right now. So we know that the points closest to y equals 4 minus x squared. No. They're not the closest to the curve. They're closest to the point 0, 2 on the curve. Y equals 4 minus x squared are negative root 3/2, comma, something, and positive root 3/2, comma, something. And so how are we going to get those somethings? Well, the answer is right here. If we know x, we know y. So root 3/2 squared is root 3/2. 4 minus 3/2 is 5/2. And symmetry says they're the same. All right? Now, I know that at least one person is wondering about this. So what I would like to do is I would like to come over here to Desmos, get rid of all this junk, and take a look at our function. If we graphed f of x and said that f of x was the root function, was equal to sqrt, the square root of, it was x raised to the 4th, minus, I think it was 3x squared, right? And then plus, I forget what it was now, jeepers, plus 4. Okay. Wait a second. Is that 4 still under that root? Plus 4. There, it's under the root. Okay? You'll see that this graph has minimums at negative 1.225 and positive 1.225, which are the square root of negative root 3/2 and positive root 3/2 respectively. If we just graph the inside of that function, that is x raised to the 4th minus 3x raised to the 2nd plus 4. While the y values are not the same, you will see that that graph also has the same x values for the minimums. And since all we're using this graph for is to find the x values, all we're using this function for is to find those x values, then we're fine just using the radicand rather than needing to use the entire function, that is the entire square root function. Is that okay? I'm hoping so. Okay. All right, so we found our critical numbers, we tested our points, we found our answers, we wrote up, make it look pretty. This brings us to the end of section 4.7. Next video will be about 4.8, which is more applications of derivatives. See you back here for that.